Welcome. This presentation will be about implementation of sliding mode controller to active horizontal seat suspension, prepared by Jarekzek, Masijewski, Krzyzinski and Krolikowski, from Koszalin University of Technology in Poland. The presentation will proceed in the following order. First, a brief introduction and purpose of the research will be presented, then the process of controller design and system modeling will be shown. This will lead us straight to the verification of system in laboratory conditions and through simulation. At the end, the short summary and conclusion will be presented. Control strategies are essential in various fields of science, including engineering, robotics, and physics. The control of a dynamic system refers to the regulation of its behavior to achieve specific aims. In this presentation, an original control strategy of an active horizontal seat suspension system is discussed that includes the sliding mode control, SMC. This technique is widely used in the control of various linear and non-linear systems such as robotic manipulators, automobiles or aircraft because it has several advantages over traditional control methods, including improved robustness in the presence of disturbances, better accuracy, and insensitivity to parameter variations. There are a lot of methods to implement the SMC controller. In general, the design procedure is based on two phases: the reaching phase where the system drives to a stable manifold in a finite time, and the sliding phase where the system slides to an equilibrium point. The MSD systems have various applications in engineering fields. In mechanical systems, the MSD is used to model the dynamic behavior of vehicles and machinery during their moving over uneven ground. In civil engineering, the MSD systems are used to predict the response of buildings and bridges to earthquakes and other natural hazards. In aerospace engineering, the MSD systems are employed to model the feedback of aircrafts to turbulence and other disturbances. However, such systems are often built for a specific technical solution in order to limit the resonant vibration or to reduce vibrations in a strictly defined range of frequencies. For this reason, there is a demand to implement the active element into a suspension system, making it more efficient in vibration isolation but also more complex. The use of active vibration reduction systems has become increasingly popular in various engineering fields to reduce the mechanical vibrations produced by machines and structures. The active element used in these systems plays a crucial role in their performance. In recent years, the permanent magnet synchronous motor, PMSM, has emerged as a popular choice for many mechatronic systems because of its several advantages. PMSMs have a high efficiency due to their permanent magnets, which provide a constant magnetic field without the need for high energy consumption. Such actuators have a high power density due to their compact design and high torque-to-weight ratio. They can operate at high speeds, making them suitable for use in high-speed applications such as automotive. Moreover, the PMSM motors have low noise and vibration levels since their smooth operation and absence of mechanical commutation. The proposed solution of an active horizontal seat suspension engages the SMC control strategy with an exponential reaching law. Exponential reaching law is a key feature of the sliding mode control, which is a robust control strategy used to control nonlinear and uncertain systems. In sliding mode control, the system is forced to slide along a particular surface or manifold, which is designed to be insensitive to disturbances and uncertainties in the system. The exponential reaching law is a technique used to ensure that the system reaches the sliding surface in a finite time. This is achieved by introducing a term in the sliding mode control law that drives the system towards the sliding surface at an exponential rate. The physical model of a horizontal seat suspension system is shown in Figure 1. The system is equipped with passive elements, i.e. a mechanical spring of the stiffness C and a hydraulic damper of viscous damping D, as well as an electric actuator in form of the PMSM motor that is responsible for generating the active force Fa. Such a force is used to reduce vibrations of the suspended body actively. Its actual value is calculated by means of the SMC controller, which receives signals from two sensors. The first sensor is utilized to measure an absolute motion of the suspended body X and the second one measure a relative motion of the suspension system. The measured signals are inputs to the controller that realizes the SMC control strategy for each feedback loop. The controller transmits an appropriate signal to the electric actuator that implements the control process in real time. The mathematical model of an active seat suspension involves one differential equation that describes a translation motion of the system, where is the mass of the system, is the damping coefficient, is the spring constant, is the displacement of the suspended body, is the input displacement of a system and is the active force applied to the system. The sliding surface is a mathematical construct that defines a boundary between two distinct regions of the system's state space. The goal of sliding mode control is to force the system to slide along this surface, which is designed to be insensitive to disturbances and uncertainties in the system. Derivative of sliding surface is needed to obtain correct desired forces and connect the control with the mathematical model under study. We consider three cases. In first case we want to suspended body to follows the input vibration signal. In second one the control strategy assumes that oscillations of the suspended body should be attenuated around its equilibrium position as much as possible. The third case of control strategy is a compromise between the previous two cases. It is necessary to introduce a weighting factor that would be responsible for combining the active forces, and, in order to obtain high efficiency of the vibration reduction and satisfying stabilization of the suspension system, simultaneously. Slideshow comparison of the desired force, red dotted line, with the force generated by using the SMC controller, blue line, with varying control aims, relative displacement of the system, A, absolute displacement of the system, B, the weighting factor, W equals 0.7, imposed on the previous two cases C. As shown in Figure 2, the desired active force is precisely reproduced by the SMC controller. In all cases the chattering phenomenon occurred, which is a characteristic feature of the proposed control system. SMC. The time histories of both forces are convergent, however the force generated using an electric actuator shows a small time delay in comparison with the desired force. Such an effect is caused by the actuation time of an induction motor. This can lower the quality of overall control strategy and in result the efficiency of vibration reduction by a suspension system. The experimental research is performed by using the test setup shown in Figure 4a. The laboratory setup is equipped with two acceleration sensors, one attached to the vibration platform and second to the upper part of a horizontal suspension where the load of the system is placed. The resistive linear displacement sensors are utilized to measure absolute and relative displacements of the system. An active element in form of the PMSM motor is used for generating the active force which influences the dynamic behavior of a seat suspension. The real-time measuring system from the National Instrument Company, Figure 4b, is employed for data acquisition at sampling rate of 1 kHz. The experimental setup also contains the B&R control system shown in Figure 4c that is programmed by means of the Automation Studio software. The control application is programmed by using the structural text language together with the OpenPLC functions coming from the MAP technology. A structure of the control system is divided to three main tasks. The first task is responsible for the operation on data from sensors such as digital filtering, scaling, and calibration. The second one allows to operate the PMSM motor, issue commands and prepares to assign the initial parameters of the motor's operation. The third one is responsible for calculations related to the control system, setting the parameters of the SMC, and generating the control signal for an electric servo drive. Simulation research is performed with the use of MATLAB Simulink package. It allows to develop structure of the system and perform numerical simulations. In order to perform the simulation tests, model parameters describing a horizontal seat suspension system had to be proposed. The spring rate of two tension springs is set to C equals 8,400 Nm. The damping factor of a hydraulic shock absorber equals to D equals 1,200 Nm and the mass of a suspended body is M equals 55 kg. Parameters of the SMC controller must be declared as well, therefore the
Μικρό ήτα
is set to 0.05 which results in satisfactorily fast reaching of the sliding phase. The other control parameters are adopted with the following values, K equals 10 and CS equals 1. The simulation time is fixed to 180 s duration. To solve differential equations included in the model, the Bugacki-Champi algorithm is employed at sampling time of 1 millisecond. The excitation signal used during simulations and experimental tests is called WN2 from previous work which demonstrates spectral properties like the white noise signal in frequency range 0.5 to 10 Hz. The corresponding power spectral densities and transmissibility functions are presented on next slide. The simulation results show that in passive system the damped resonances occurred at frequency range of 1-2 Hz. Such a passive system tends to amplify the vibration transmitted in the low frequency range while the vibration damping effectiveness increases for higher frequencies, red lines. The transmissibility function of an active system is close to 1 when the relative stroke control is applied. It means that such a system well follows the input vibration signal, but in this case the vibration attenuation of a suspended body is rather poor, blue lines. While the absolute displacement control is activated, the transmissibility function shows the most effective vibration reduction capability of a horizontal suspension, green lines. Using such a control strategy, the damped resonance of a corresponding passive system can be fully eliminated. The vibration transmission through an active suspension with the weighting factor equal to W equals 0.7 points out a compromise between the mentioned above versions of the proposed control strategies, yellow lines. This control policy increases both the isolation of a suspended body against harmful vibrations and the ability to steer the vehicle when it's moving over rough terrain. The experimentally measured transmissibility functions show similar trends like those which are obtained during simulation. The passive system demonstrates its resonance frequency at about 1-2 Hz while the amplification of damped resonances tends to 1.2, red lines. The transmissibility function of an active system with the relative stroke control slightly differs from the simulation results, blue lines. Excessive increase in vibration amplitudes is achieved within the frequency range 3-10 Hz. Such astonishing results may be caused by the increased friction of a suspension mechanism under active vibration control. However, as previously noted, the trends of each measured transmissibility function are like the corresponding simulated ones. As in the simulation, the best performance in vibration reduction is occurred when the minimal absolute displacement, green lines, is chosen as control objective. A compromising solution corresponds to the weighting factor of W equals 0.7 and the transmissibility function of such a system is located in between the other configurations of an active seat suspension, yellow lines. As shown in table, the maximum relative error between simulation and experimental results approaches the value of 39% in terms of the relative stroke, RS, and 30% in case of the seat factor. Such errors may be occurred due to significant differences between the actual test object and its simulation model, that is the presence of friction in a suspension mechanism, neglecting the end-stop impacts limiting the relative displacement of a suspension system, and the use of a linear damper characteristics instead of its nonlinear behavior. Nonetheless, the experiment and simulation show that the best reduction of mechanical vibrations occurs when the system tends to stay in equilibrium position. Absolute displacement of the suspended body is minimized. An application of the weighted active force in terms of minimizing the conflicted system requirements allows to increase the effectiveness in vibration isolation of the suspended body while maintaining the relative stroke of a suspension system on acceptable level. This presentation shows a mathematical model of an active horizontal seat suspension system with the sliding mode controller, as well as its verification through simulation and experimental research. The sliding mode controller is responsible for sending feedback signals to the PMSM motor in order to generate the force required for keeping the system under specific control conditions. The SMC can effectively handle these disturbances and ensure passenger comfort. The SMC has a simple implementation, requiring few or no additional sensors, making it a cost-effective solution. This simplicity makes the SMC an attractive option for industrial applications. It also has a fast convergence rate, ensuring the system's stability and reducing the settling time. This feature is particularly advantageous in horizontal seat suspension systems, as it improves passenger comfort. One of the main drawbacks of the SMC is chattering, a high-frequency oscillation that occurs when the system switches between two sliding surfaces. Chattering can cause mechanical wear and noise in the system, reducing passenger comfort. The performance of the SMC depends on the selection of tuning parameters, which can be challenging in horizontal seat suspension systems due to the nonlinear dynamics and uncertainties in the system. The tuning process may require extensive experimentation and may be time-consuming. In the future activities, parameters of the SMC controller should be optimized and the stability analysis of a closed system should be executed. The presented model and results can be useful for developing the control strategies for similar mechanical systems. Thank you for your attention.